All right, so this is 152, and semester's coming to an end. This is Chapter 12, Part 2, or the last part of Chapter 12. There's just one more chapter after this, and then the last class when I'm not going to add any new material. So let's take a look at it. We're down to more about Windows. Windows is, of course, a very important target for investigation. And so we're going to talk about memory forensics and persistent sessions. So, interactive sessions, controlling Windows machine like you log on at the keyboard. Logging at keyboard is one way, or remote desktop, or perhaps screen sharing. Not that common, but it can be done. So, link files are what Linux calls them soft links, I think, or hard links. I forget, there's a difference between the two. But the point is, it's a file. It appears like a file on your desktop, but it's really just a pointer to another file somewhere else. And so Windows creates links for every open file to populate the recent files, and there's a separate list of those in each user profile. So here's where they are in app data roaming, which is where most personalized parts of your user profile are. And in those link files, you'll find the full file path, the network share name, the size, modified, accessed, and created timestamps, and an object identifier, so you know a lot of information. Somebody has been using that file recently, the sort of thing you want to know. So they can show what you've done, what files are accessed, and in what order. So you can construct a timeline. And then there's the jump lists. If you right-click any of these buttons at the bottom of the taskbar in Windows, it will show you the recently used items of that type. So on this it'll show you the recently accessed folders, and if you right-click on Microsoft Word, it'll show the recently accessed Word documents and so on, and that's of course quite useful. And those are stored in the same place, app data roaming, and these automatic destinations and custom destinations at the end. Like so many Microsoft things, it's not human readable, and you need a special tool to pick apart their proprietary binary format, but the tools exist. And the recycle bin, of course, when you delete things, if you didn't delete them from the command prompt or with shift delete or from removable drives, they go in the recycle bin, and they wait there until the recycle bin consumes a certain percentage of your hard drive. I think it might be 15%, and then after that it throws away the old stuff to make room for the new stuff. So the idea is you get a second chance to get back stuff you deleted. But of course, that's handy. The stuff, if important evidence has been deleted, you can find it in there. And there's a tool to list what's in the recycle bin with all of its timestamps and so on. So that's one tool to help you do that. And Velociraptor, of course, can do it too. It has a recycle bin acquiring tool that will give you the same kind of list of everything in the recycle bin with the metadata, like the timestamps, which will help you piece together, what has been thrown away, when was it thrown away. Just checking for comments in the Twitch. All right, good. And all right, and so memory forensics. The RAM on your machine has the records of all your current activities, current network connections, current downloads, running processes, loaded drivers, often user credentials. As I've done in projects in the forensics class, if you have a password manager, all the passwords are just sitting there unencrypted in RAM. So it's a place where pen testers look pretty fast. And various other things are in RAM. It pertains to the current operation of the machine. And in instant response, the RAM is usually where you get most of the evidence you need. The hard drive is not really the number one target. RAM is for getting data that's going to help you resolve an incident. Now, there's physical RAM with RAM chips, and then there's a page file. Windows will just randomly decide to move stuff from memory into the page file and from the page file back into RAM without any rhyme or reason to it. So it can be very strange. But Windows is intended to always work with a page file, so this is another place where some data from RAM does in fact end up in practice. Then there are crash dumps. When your machine crashes, it might create a crash dump file, depending on how your machine is set. By default, it only dumps the kernel memory, which is not very useful to a forensic investigator because the kernel memory doesn't include very much user data at all. But if you set it to make a complete memory dump, this would be more useful, but then larger. that shows up in the crash dumps folder in local app data. And, the complete memory dump would be as good as a forensic image of memory, but it's rarely turned on. And, this is not generally used for an investigation, but it might be used if whatever tool the bad guys are using is crashing your server. Then these memory dumps might help you figure out why. Checking for comments. No new ones. Okay. So the hibernation file also saves the full contents of RAM on disk. Now it's compressed, which is nice in modern versions of Windows, and volatility can parse it. And volatility, I think, is included in Velociraptor, but I'm not quite sure. Volatility can parse through these things and recover all sorts of things about each process. It does have to know exactly which version of Windows you're using, however. And this is what it looks like if you run volatility natively. You want a list of processes. You have to tell it the profile, which has to be exactly which version of Windows you're using and which service package it has. And then it'll go through a memory dump and give you a list of all the processes of the type you would be able to get from the command line if it was a running system. All right, let's take a look at a Kahoot, which should be here, 12C1. All right. All right, maybe that's it. All right, if you right-click the taskbar icon, what do you see? The jump list, they call it, the list of files you see. This was a step up from like Windows XP. Instead of having one start button, you had sort of a whole row of start buttons at the bottom of your screen. All right. All right, which one do you only get from a live acquisition? Yeah, RAM. You can only get from a live acquisition. If the power's off, the RAM forgets everything. All right, which item contains the entire contents of RAM? Hyperfile does. The crash dump can, but it's usually not configured that way. All right, which one only contains kernel memory by default? Yep, that's a crash dump. By default, just the kernel memory, which is useful if you're trying to debug a faulty device driver, but not usually for forensic investigation. Good. So, All right, handles I mentioned before. When you open a file to read or write in C, you have a handle. It is equal to the return of the opening function, and then you use it to refer to that object later, so you can read to it, write to it, close it, things like that. And mutants or mutexes are mutually exclusive items. I heard this in a podcast recently. This is a mark put in the memory that can be seen by other processes so they can send a signal to them. To mark that I'm using this file, you better not use this file until I'm done. But for malware, it's done to mark an infected box so the malware knows not to reinfect it. So Zeus, a famous piece of malware that was around for quite a while, would create this thing called a Vera 2108. And by the way, it is pretty common for malware to give it a name that makes it sound like an antivirus product just to hide it. All right, and if you go to Notepad and look at the handles, you'll find various handles here, default, known, DILs, and various other ones here like Wednesday 0 and so on. It just has various things that have been stored, things that are in use by Notepad. Velociraptor can detect mutants. You can just pick it up with Windows, detecting mutants, because they're very often of value in an investigation. So each process has its virtual address space, including some RAM and some space in the page file, and the OS swaps data in and out of the page file. And there is a kernel data structure called the virtual address descriptor tree that shows what memory is being used by each process. There is a tool for that called VMMap from sysinternals that will show you exactly what part of memory is allocated to each process. It is pretty complicated how Microsoft Windows uses memory. And if you really want to get a headache, read through modern heap exploits for Windows. The heap is pretty complicated, and exploiting it is pretty complicated in Windows. And again, Velociraptor has a thing that harvests the VAD. So you can get the memory regions of each running process. I'm going to take a look for comments. And there are no new ones. All right. So, to detect malicious DILs, libraries that might be attacker created, check for valid digital signatures. Ones that don't have a signature are suspicious. Of course, you can check the hash values at a known bad table like VirusTotal. And you can look for evidence of tampering attacks like the kind we're doing in the malware analysis class, where you loaded DIL surreptitiously. Another thing that might help you. And here's the DILs for Notepad. Even a normal program, a very simple program like Notepad, loads what looks like about 20 libraries, all sorts of things, kernel 32 and shell 32 and Olay 32 and so on. These are all libraries being used by even the simplest Windows program. And of course, as always, you can do it easily in Velociraptor. Windows System DILs will enumerate all the DILs loaded by running process, including hash value and certificate information, which is just what you need in order to investigate that DIL and see if it's known to be malicious. Network connections are in memory, loaded drivers, console command history, strings, if been typed into Notepad or any other program, and often credentials. I saw a comment here. Oh, good. Okay. Identifying yourself for this. This is good. All right, good. So, all right. Now, the page file has no intrinsic structure. It's hard to search through. One thing you can do is just run strings on it to find readable strings. You might see all sorts of suspicious things in the page file that the person has not really been visiting. They might have been put there by antivirus and so on. This is a mistake I heard one of my forensic instructors tell. They actually took a person to court and tried to prosecute him for visiting a bunch of porn sites on a classroom machine, and it turned out that there was just a list of URLs in the anti-malware software of bad sites not to go to. It was not evidence that this person had been to those sites. That list was just in the antivirus software, so this is a thing to be aware of. Just because you find something on the machine does not mean it has been used for a bad purpose. You got to be much more careful in interpreting it. All right, so common in-memory attacks are process injection and hooking. These are ways malware gets on the machine. Process injection is the where you cause injecting process loads another process to run malicious code. This is popular because you don't change any disk files, and a lot of antivirus only looks at disk files. So keeping it in memory is a way to hide from defenses. The injected process would have no evidence indicating which process created it. There is no source or caller ID or anything in a process telling you which other process launched it. So you can do it with the Windows APIs if you have administrator rights, force the target process to load a malicious DIL, or you can directly write malicious code to the target memory and invoke a thread to execute it. This is a trick I've used a lot to sneak past antivirus. I load malicious stuff in memory as data so it doesn't get triggered, then change the properties of that memory region and execute it. And that'll fool most antivirus. It's an old trick, but it's still fooling them. Then there's process replacement, where you have a legitimate executable, and then you change the contents of memory while it's there and just unsuspend it. This is pretty terrifying and important to understand. This is why when you go into Process Explorer, you can examine the strings in a process, and you can separately examine them on the disk and in memory. And they should be the same, but if they're not the same, this is what's happened to you. It has launched from a disk file and then later been changed to contain some other program, which continues to run with the privileges of the original legitimate program. All right, so you can look for memory sections with read, write, and execute permission. That should not be allowed in any modern operating system. That's too dangerous. The one main security rule is write or execute, but never both. And I mentioned processes that don't match the corresponding disk files. So here's sysmon detecting an injection. Create remote thread detected. So it just detects somebody launching a remote thread. I'm not quite sure how clear this is, but this is one thing, one clue for injection. All right. It's not as clear as like an intrusion detection system, but it'll give you a clear answer whether this is malicious. All right, so persistence mechanisms are the mechanisms that make your malware relaunch when the machine is rebooted, so you maintain persistent control of it. So you need some kind of persistent mechanism. Auto run keys we've seen, DIL load order hijacking, so it automatically loads the library again in something that automatically launches, that sort of thing. Hooking is another way. Hooking is a trick, for example, for a keylogger. You're running a keylogger. Every time you press a key, I want my malware to hear about that, so you can intercept, modify, and view events. There's a lot of API mechanisms for this because it's a thing you might want to do. You might want to buy a special Bluetooth keyboard or something, and then every process on the machine should know to connect to that keyboard and so on. So a lot of things use this. Antivirus, for example, hooks everything before you open a file. It says, wait, you double-click on a file, and it says, wait, before you open that file, let me run my code first to check it and see if it's malicious, that sort of thing. Now, malicious hooking is essentially rootkits. Rootkits hide files and processes, registry keys, network connections. Keyloggers can listen whenever a keyboard event occurs. They can also use an asynchronous key state to constantly check the up-down state of keys, which is a more difficult way to detect key presses. So you can manipulate a process's import address table so it calls malicious functions instead of legitimate system functions, or you can try to hook kernel structures like the IDT or the SSDT. But as I said, I think last time, or it might have been in the other class, this is the old-fashioned way rootkits worked up until Windows Vista in 2008, but since then it is very difficult to modify either of these things. So this is not a modern technique to get in. Yep, the kernel patch protection stops on the modern versions of Windows. So I haven't heard much about kernel mode rootkits in several years. Zeus was on a system infected with Zeus. This is going to show an inline hook to catch HTTP send requests. So here, user mode inline trampoline hook, hooking wininet.dil, and somewhere it's going to tell me the particular module, HTTP send request A. So now every program that tries to send an HTTP request will run through this poison code instead of the original code, so it will do something to the network connections chosen by the Zeus rootkit. I'm not sure what that is, maybe steal passwords you type into a web page or something like that. And so there's a lot of tools to analyze memory. Velociraptor can do it to some extent. That's mainly what we're going to use. These other tools are volatility was very popular. It's hard to use at the command line, but it's the guts of Velociraptor and also autopsy. And memorize is another tool people use. There's a lot of them to analyze memory. All right. Let's try another Kahoot. 12C2. There we go. All right, a kernel data structure that shows how memory is used by each process. The VAD, virtual address descriptor or something like that, that's what it is. All right, which one will include malware signatures even when there's no malware in the system? The page file includes random data from memory, and your antivirus is going to have some virus signatures in memory. All right, which one is most likely to be malicious? Yeah, process injection is much less. These other things are perfectly normal. That's an unusual thing, likely to be malicious. All right, which one is used by malware to prevent reinfection? Mutants, marks in the memory that can be read by other processes so they can know that the machine is already infected. All right, so other persistence mechanisms. Startup folders used to be in Windows XP. You could right-click the Start button and explore it. I think it's harder than that now, but there is a startup folder for each user, and any shortcut you put in there will automatically launch when that user logs in. Recurring tasks, I think these are scheduled tasks, with Task Scheduler, and then you can, in principle, if you're really hardcore, you could modify a system binary that's used by the operating system, one of the libraries or processes that automatically launches, to do something extra. That's not very easy and not very common because it would depend on that exact version of that file, and a Windows update might trash it. Sticky keys is a user accessibility feature. You can press, I think, the shift button 5 times, and then an on-screen keyboard will pop up, and you can modify that to open a different file. And then DILD loader hijacking, we talk about quite a bit in the malware analysis class, tricking a process into loading the wrong library. This is the most common way to launch malware. So here's where the startup folders are, pretty deep. The all user startup folder is here, and the user specific startup folder is in your app data roaming and so on. Yeah, recurring tasks, this is scheduled tasks. That's what I thought. You can do it with the command line commands at or SCH tasks, or you can open Task Scheduler, which is a graphical tool to manage these scheduled tasks. Like I say, modifying a system binary is possible, but it's pretty nasty. However, if everything was signed, it would be impossible, but not all legitimate system binaries are signed, which is kind of a shame. It would make a lot more sense to sign them all and enforce signature everywhere, but Windows does not do that. So you'd have to very carefully modify it, and it's very likely, if you're sloppy, that you'll cause the machine to crash. That's why this is not very common, but it can be done by more sophisticated attackers. It would be a whole lot easier to just replace a whole file or library that's not really important. So Windows File Protection was a defense on this. Now we have Windows Resource Protection, which is more resistant to tampering. And both of these try to stop anybody from modifying essential system files. Now there are third-party utilities you can put on, the most famous one being Tripwire, that will store a hash value of every system file and then alert you if any of them change. And this is what I've been advocating for a while, that we should have on our firewalls, because now firewalls are targets for attack, and they're getting infected, and they currently have no defense. And mainly what you want on a firewall is to be 100% sure that all it's running as intended. So you really ought to have tripwire type protection, in my opinion, where you have some kind of automatic process that checks to make sure that every file has not been modified and does something if anything is modified, like perhaps restart and restore everything from a secure boot process back to its clean state. But currently, we don't have that in any firewalls I'm aware of. Sticky keys I talked about. This is the thing. SethHC is the accessibility thing that's supposed to pop up the on-screen keyboard for people who have to use a different way of typing things in. But you can replace this executable with another one, and then it'll pop up any other executable you want. A common one is to put cmd.exe there, and then you can press Shift 5 times and get a command shell before you log in. So you get the ability to run code on a machine without properly logging in. I think modern Windows have some defenses against that. Yeah, Vista and later versions supposedly has been blocked, but there is another way to do it by setting a registry key, a debugger key. It's not as simple as just replacing one executable anymore, but it still can be done. All right. And Windows Defender will now detect when you're doing that, so you know. It's a cat and mouse game. The bad guys always find another way to do this, and the good guys find another defense. All right, DIL load order hijacking. This used to be a huge problem in Windows NT. It's still a pretty bad problem. You can, unfortunately, the most common thing people do on Windows machines to get a command shell is they click Start, Run, CMD. That right there is not the best practice. You type in a command line, the name of a program, you didn't include the extension or the path. So now Windows has to hunt for that file. Do you mean cmd.com, cmd.exe, or cmd.bat? Do you mean for it to be in your profile folder, or in C or C Windows or C Windows System or other places? It has a whole pattern of where to hunt for that file, just like Linux does in the path, and so it hunts for it. So all you have to do is put a file in a place that's earlier in the search pattern, and you can trick it into running the wrong file. That's called DIL load order hijacking. There is a defense. The known DILs registry key lists the exact location of known DILs and makes sure they're all loaded from C Windows System 32, where they should be. And that's good, but not everything is in there. This is one of the many weaknesses in Windows. So here you see known DILs. Here's the path, HQ local machine, current control set, session manager, known DILs. And here you see a lot of the common libraries like kernel 32 and user 32 are in here, so they will never load from any other directory. But this is very far from the complete list of libraries. So only certain libraries are protected by this. If you don't have the DIL, it goes through this search order: the directory where the application started from, the current working directory, System32 system, system root, then the path environment variable entry. So it's hunting all over the place for it, and therefore it is pretty easy to trick it into loading the wrong file. All right, so it works, except if the DIL is specified in known DILs, and as long as the legitimate DIL is not higher in the search order. And what Microsoft has said for years is that it is a best practice to always refer to everything by the complete path without making it hunt for things, which is more work but much safer. All right, so let's try another Kahoot. We check for comments first. There are no new comments. All right, we'll do the last Kahoot. I think for 20 years, Microsoft has been saying you should type start run /Windows /System32 /cmd.exe, but I don't think anybody does it. That's a lot of extra work. However, to be fair, I never launch a command shell that way anymore. I just go to the search box and type in command and it opens up in the search menu, and that's safer. All right, so what technique produces job files? It's recurring tasks that are also called scheduled tasks that creates these files called job files. That's how it works. All right, what technique uses app data? Startup folders are deep down in the app data directory. All right. What technique requires pressing Shift 5 times? That's sticky keys, bringing up the accessible keyboard or perhaps some other file. And what technique is prevented by WRP, Windows Resource Protection, I think. That's when they modify the system binaries. Perhaps that's the same as Sean L. I think I'm going to assume that's the same as Sean L. Unless you stop me. Time and step.